It goes without saying that proofs by contradiction can be quite tricky, and that starts with the fact that, well, in the beginning we have to assume that something which should be correct is not correct. In addition to that, in order to prove by contradiction, we carry out an algebraic process despite the fact that we know that at some point it is not going to work. So that in itself can be quite confusing. And also there are many types of proofs by contradiction. In this video, we're going to go through proofs by contradiction which involve parity. What does that mean? It involves even and odd numbers. We get to prove or disprove something using the fact that a number is either even or odd. And we're going to start with developing the 5-step process, or going through the 5 steps that you need to carry out in order to prove by contradiction. Then we're going to prove that no number can be both even and odd. And lastly, we're going to go through these 2 exercises that you see in your screen. Do know also that you can find the exercise list for proofs by contradiction in the description of this video. So let's start with the 5-step process. The steps that you need to go through start with 1, which is to state the proposition. You're going to clearly articulate the statement P that needs to be proven. For example, P could be log of 3 base 2 is an irrational number, or maybe if n squared is a multiple of k, that means that n is a multiple of k as well. So these are just a couple of examples. Alright, so what comes after that? Step number 2. And this is very particular to proofs by contradiction. We're going to assume that the negation of P is true. And negation or negating is the most appropriate use, the most appropriate word to use over here. Now, what is the negation of a statement? We can use a few examples to address that question. So for example, what is the negation of, and by the way, you need to be extremely careful with what is the negation of given statements. For example, let's say that the statement is all cats are black. The negation of that statement is not all cats are black, or there exists at least one cat which is not black. For the statements that I wrote previously, not B, which can be written like this, is respectively log 3 base 2 is not an irrational number, or in this case, you could safely use is a rational number. So this would be equivalent to saying, for example, what is the negation of this cat is black? It will be this cat is not black, which means this number is not an irrational number. And numbers that are not irrational, well, they're rational. In the second case, we have an if clause, an if statement. We're going to address how to deal with if statements in another video. What will be an example? It will be something like, if a student studies, then he passes the exam. The negation of that is the student studies and he does not pass the exam. Number 3, we're going to develop the proof. What do you mean by developing the proof? You're going to use the assumption not P along with either an algebraic process with established facts or axioms to derive further logic conclusions until you get to a contradiction, until you get to something that does not make sense. And this is, of course, the most difficult part of a proof by contradiction. All right, so we're almost done. Step number 4. As you're going through the process, you're going to also identify the contradiction. So you need to clearly state where the contradiction emerged or where you got to a contradiction. So let's suppose, for example, that you're trying to prove that something is bigger than something else. And then in one of these steps, you get 1 is greater than 2, for example. This is just a silly example. In that moment, you got to a statement which, well, it's simply not true. So that's when you have to write which is a contradiction. And number 5, the last step, is to write the conclusion. Now, the conclusion in a proof by contradiction is much smaller than the conclusion in an induction proof. You just simply have to write, therefore, by contradiction, that P is true. And you substitute P by whatever statement you're trying to prove true. For example, in the first example that we mentioned here, therefore, that log 3 base 2 is an irrational number. So you write, therefore, by contradiction, P, whatever P is true. And P, just to use an example, the first example, log 3 base 2 is an irrational number. All right, so now that we know the 5-step process, and before we tackle these two exercises, we're gonna prove something that's the foundation of this type of strategy. The strategy of using the fact that no number can be both even and odd. And that's exactly what we're gonna prove. We're going to prove that no integer is both even and odd. So let's call this an extra exercise. Prove by contradiction that no integer is both even and odd. Now we're gonna apply the 5-step process. Number 1, our statement P is no integer is both even and odd. Number 2, we're going to assume not P, which can be written like this or just as not P, which means that we're going to assume there exists an integer A, and you can call it anything, of course, which is both even and odd. Number 3, and by the way, you don't need to keep writing steps number 1, 2, 3, 4, 5. You can just go through the exercise. This is just me being a little bit more detailed. Now, what is step number 3? If A is even and if A is odd, we can represent A in 2 different ways. A is 2 times k, and we write an even number as 2 times an integer. That's how we represent even numbers. And given that A can be odd as well, we're going to write A as 2k plus 1. Now there's just a small detail here that we don't know if these are consecutive integers, so we're not going to assume that, okay? So we have A as 2k1 and also as 2k2 plus 1, provided that, of course, both k1 and k2, they are integers. Now, given that we're talking about the same number, we can equal 2k1 to 2k2 plus 1, which means that 2k1 minus 2k2 is equal to 1, which also means that 2k1 minus k2 is equal to 1. Therefore, the difference between these two integers k1 and k2 is equal to 1 over 2, which is a contradiction. Here lies the contradiction. The difference between two integers is an integer, or should be an integer. So that's exactly what you should write, which is a contradiction, given that the difference between two integers should be an integer. Therefore, by contradiction, the statement P is true. And if you already defined capital P in the first step, which is exactly what I did here, you don't need to rewrite it. You can simply say, by contradiction, P is true. So there you have it. Now we're going to move to the 2 examples. We are going to prove by contradiction by applying the fact, by using the fact that no integer is both even and odd. All right, so example number 1. Prove by contradiction that a cubed minus a plus 1 is odd for all positive integers, a being a positive integer. Now, as mentioned before, it is useful to restate what P is, what the proposition is. So let B be the following statement: a cubed minus a plus 1 is odd for all, and by the way, this symbol right here means for all positive integer a's. Now, we're going to assume, for the sake of contradiction, that a cubed minus a plus 1 is even, which is the negation of P. Now, we're going to break this into 2 possible scenarios. If a is an even number, we're going to analyze that possibility, or if a is an odd number. Now, in this case, we can use the same k, because these possible events do not happen at the same time. So we can call one case 2k and the other case 2k plus 1. Now what happens if a is equal to 2k? In that case, a cubed minus a plus 1 is 2k cubed minus 2k plus 1, which is equal to 8k cubed minus 2k plus 1, which is, factoring out a 2 in the first 2 terms, equal to 2 times 4k cubed minus k, close parentheses, plus 1, which is odd. We have a sum of an even number with 1, which produces an odd number. Therefore, given that we assumed that a cubed minus a plus 1 was even, well, we got to a contradiction. Now let's analyze the other case. What if a is an odd number? Well, in that case, a cubed minus a plus 1 is equal to 2k plus 1 cubed, and yes, you will have to expand this, minus 2k plus 1 plus 1, which gives us 8k cubed plus 12k squared plus 6k plus 1 minus 2k minus 1 plus 1. We can cross out a couple of 1s and simplify this 6k with the negative 2k, and this gives us 8k cubed plus 12k squared plus 4k plus 1 and as you can see already, this is not an even number, this is an odd number. So we write which is odd, therefore we get a contradiction, or we get to a contradiction. And the conclusion, by contradiction, our statement P is actually true. And how did parity help us in this exercise? Well, we analyzed the only two possible cases for A. Either A was a even number or an odd number. And breaking it down into these two cases allowed us to conclude by contradiction that actually a cubed minus a plus 1 is odd for all positive integers. Now let's tackle exercise number 2. Prove by contradiction there are no positive integers a and b, with a being odd. And by the way, this information right here will not change when you consider the negation of this statement. The negation will involve a still being odd, such that a plus 2b is equal to the root of 8ab. So let P, the statement P, be the following. There are no positive integers a and b with a being odd such that a plus 2b is equal to the root of 8ab. Now we're going to negate this statement. So we're going to assume there exists positive integers a and b with a being odd. This is a prerequisite for the proof, such that a plus 2b is equal to the root of 8ab. Given that we're talking about positive integers and we're assuming that this equation is true, we are going to square the left-hand side and the right-hand side, which gives us a plus 2b squared equal to 8ab. Now, when we get to this point, we can analyze the number parity for a and b. Well, actually only for b, because we know that a is odd. So we're going to analyze the parity for b. We're going to assume that a is odd because, well, that's our assumption, and we're going to break it down into two possible cases. What happens when b is even? What happens when b is odd? And we're going to, using a little table, get to a contradiction. Now, drawing a simple table, we're going to break it down into two cases, when b is even and when b is odd. And we know that a is odd. Well, what happens to a plus 2b when we consider a to be odd and b to be even? Well, in that case, we're going to have an odd number plus 2 times an even number, which by itself is also an even number. When we add an odd number to an even number, well, the result is odd. Now let's consider the second case. Let's say that b is odd and, well, a stays odd. Then we have the sum of an odd number plus an even number, given that 2 times an odd number gives us an even number. Therefore, the result is still odd. And what happens when we square an odd number? The square of an odd number is still odd. And over here, you can just picture an example such as 3. When you square 3, well, 9 is still odd. This is also something that you can prove. If n squared is odd, that means that n is odd. And if n squared is even, that means that n is even. We're going to go through these proofs also. But let's just leave it as it is, just so we can finish this exercise. So what we did over here was to evaluate the parity of a plus 2b squared. Now, the left-hand side, which is a plus 2b squared, is always odd. It doesn't matter if b is even. It doesn't matter if b is odd. The left-hand side is always odd. Now, the right-hand side, though, is even. It's 8 times a times b. The fact that we can factor out a 2 shows us that this is an even number. The right-hand side, I mean. So this guy right here is even. And we have a contradiction. The left-hand side is odd and the right-hand side is even, given that it can be written as 2 times 4ab. Therefore, we have a contradiction. By contradiction, we can state that P is true. And do remember that P is, there are no positive integers a and b with a being odd such that a plus 2b is equal to the root of 8ab. So there you go.